Today I want to talk about radio communication as a system. Radios themselves are normally manufactured. Within each radio you have a transmitter and a receiver. The radio you're trying to communicate with is over here. Now I'm ignoring everything else that might be in between. Hilltop repeaters or network systems. So we're condensing this down to just simply two radios. They're going to communicate with each other directly. Now, the manufacturer of that radio and the manufacturer of that radio might be different, but the manufacturer has control here. So the transmitter has a certain power and the receiver has a certain sensitivity. So I'm going to actually put some numbers here. I'm going to say that the transmitter is 25 watts and the receiver is neg 120 dBm. And they're fairly typical figures for transmitters and receivers. So we're going to go 25 watts and a neg 120 dBm. Now, of course, obviously you can have a radio failure, but in terms of this being a system, they're the primary building blocks to it. Now this radio will have a source of power, as will this one. Now, if the power is incorrect, if it's supplied with too much energy, like it's a 12 volt radio and you put 24 volts into it, 9 times out of 10 it will blow up. If it's a 12 volt radio and you're not delivering 12 volts to it, the radio will turn off. That's also fairly typical for radios. With this system, the one thing that the radio manufacturer can't control is the antenna installation. Now, we have no control over this environment. The path loss is entirely dependent on the environment. The one piece that technicians or radio installers or radio engineers can control is this antenna plant. A correctly installed antenna makes an enormous difference to the overall quality of this system. And it's the one thing that the radio manufacturers don't have control on. Unfortunately, it's the one big thing that I'm finding on a regular basis which I would consider to be a fail. Incorrect installations or incorrect antenna usage. With an incorrect antenna, this entire radio system fails. Or it may not fail, but it just doesn't perform particularly well. Now, from a user perspective, a lack of performance is normally perceived as a lack of range. My radio will work when the other guy is only a couple of kilometers down the road, but he very quickly gets out of range. That's the user perception. Now, what we're going to do is we're going to enlarge on this particular issue with respect to aerials and hopefully break it down a little bit and describe a little bit more about what should be occurring here, because as an installer, this is the primary piece that makes the difference between a good installation and a poor installation. Okay, aerials. What we're going to do is we're going to break aerials down into two subsets. The first subset requires a ground plane. The other subset is ground independent. Now, this is a fairly fundamental thing that I'm finding all the time. Ground independent antennas are usually slightly more expensive than those antennas that require a ground plane. What I'm finding a lot of the time is antennas that require a ground plane are fitted onto vehicles in a location or in a way that the antenna isn't given a ground plane. Now, we'll talk about ground planes generically for a little bit. If we've got an aerial like that, that's a quarter wave whip, which is the most generic antenna. It requires a ground plane. The size of the ground plane, I use a rough rule of thumb, and that rough rule of thumb is you take the height of the quarter wave whip and you draw a circle, and it's the requirement for the size of your ground plane. Now, on a vehicle, there are some quite good ground planes. We'll just talk about a vehicle for a moment. You'll have to ignore my terrible drawing. Here's a car. We've got a car roof, a windscreen, a bonnet, a rear window, driver's door, window. Here's a car. Now, what we're looking for is we're looking for a ground plane, and we need a ground plane based on the height or the active part of the antenna and using it for a whip. You know, on a car, one of the best places for it is right in the middle of the roof. There's always a temptation to install a quarter wave whip on a front mudguard, or perhaps back here. The problem that you encounter if you use either of these locations is you can't get a complete ground plane. On the roof you can get the circle that you require to provide you with a ground plane. Out here on the bonnet, you can get a half circle over the top of the bonnet, and then out here we've got fresh air. There's nothing out here. So I would say wrong location for a quarter wave. Same here. We can get over the top of the bonnet, over the top of the boot, we can get a half circle, but over this part, no, you can't. You only get half a ground plane. Wrong location for a quarter wave. And that's a very typical issue that I'm finding with installations on cars. We'll talk about trucks for a moment. Here's our truck. And again, you'll have to excuse the terrible drawing. In the middle of the roof, we have a ground plane. That'll work okay. Out here on the bonnet, again, 9 times out of 10, we only get a half a ground plane. So it's an inappropriate location. But the nasty one that I find quite regularly on trucks is mirror brackets. So we've got a mirror, or a bracket, which is sticking out to the side of the vehicle here. Let's just draw a truck from a different perspective, shall we? We'll look at the truck from the front. Here's the top of the roof. Here's the bonnet. The engine's in under here. There's the windscreen. And out here we have a mirror bracket with a mirror fastened to it. Lovely place for an aerial, you might say. We'll put our aerial there. Except there is no ground plane. In fact, there's very little ground plane. So, inappropriate for a ground plane aerial to be mounted on a mirror arm. Now, ground independent antennas, these ones over here, have an advantage. They're normally slightly more expensive than these ones, but these ones have an advantage. If you have a ground plane, you can mount it above it. I'll just draw my ground independent antennas like this. That's appropriate. It will work just fine. You can also make them, let's take this ground plane right away and put a mirror arm here. Here's the side of our truck. It's bolted on over here. Here's the truck mirror, bolted on over here. Now, ground independent antenna mounted like that, that will work fine as well. Now, what I'm discovering is this is my belief. What I'm discovering here is I believe there's a complete lack of understanding between ground independent antennas and those aerials that require a ground plane. And that complete lack of understanding results in very poor aerial installations. And the most typical problem is antennas that require ground planes installed in a location where a ground plane is required, but there isn't one there. So the aerial performs extremely poorly. Here's a perfect example of a quarter wave whip mounted in an inadequate situation, or it's an inappropriate aerial for the situation. What we have here is we have a quarter wave whip. In this location we have an adequate ground plane provided by the bonnet, and out here we have fresh air. The most common ground planed antenna is a quarter wave. That means the height of this active section of the antenna is a quarter wave. And it's a quarter wave at the frequency of operation. So you need to know the frequency. If you do not trim this antenna to length determined by the frequency, then that won't work properly. It's a fairly fundamental thing. You can't simply take a whip antenna out of the store and bolt it on something. It won't work. This antenna, the length of this antenna, you have to look up a chart that will give you a physical height in either inches or millimeters, dependent on the frequency you wish this antenna to operate at. Now that's very fundamental. The crazy thing is, I find a lot of antennas that have just simply been taken out of the store and bolted on. Obviously it's not been tuned to a quarter wave. It gets worse if it's not fitted even on a ground plane. And that's a fairly fundamental thing we need to do. We need to make sure that we're trimming the height of this antenna as a quarter wave dependent on frequency. And there are plenty of published charts to give you this height either in inches or millimeters. Now a ground independent antenna, and I'll draw it like this, and I'll draw it as a bracket like that. There is no ground plane here, but the same thing applies. We need to know the frequency of operation. That's important because that frequency of operation will probably require this antenna to be trimmed. So what you're going to do is you're going to cut the end, well actually the end you cut off. Sometimes it's actually the tip. Some antennas require the tip to be cut off, so you'd be cutting the tip down. Other antennas you would actually remove a grub screw from here and you would actually cut the base of this whip. Depends entirely on the antenna concerned, but you will be cutting this length between there and there to a specific length based on frequency, and the manufacturer of the antenna will actually give you a chart to tell you what that physical height there is. You can also go online and do some research and look it up if you wish, but the important point is, again, you cannot simply take an aerial out of the store and bolt it somewhere and it will operate, because it won't. Most antennas actually have a tuning range. The one example which I can give for New Zealanders at least is the Citizens band. The Citizens band in New Zealand operates at 26 megahertz and it's AM, and you can purchase pre-tuned quarter wave whips, and you can purchase pre-tuned ground independent antennas. Most other antennas that you come across require the antenna to actually be trimmed, and they will come with a trimming chart or some form of instruction. Okay, the other issue with respect to aerials and poor installations of these aerials is a lack of understanding about how an aerial is adversely affected by adjacent structure. And this issue affects all aerials, whether they require a ground plane or whether they're ground plane independent. Now I'm going to put some examples, I'll draw some sketches on the board in a minute, and tell maybe a story or two. This kind of situation is quite interesting. Here's the roof and side of a truck. This is the roof and this is the side. And I saw one of these the other day which didn't impress me too much. The antenna was installed here.
Okay, we're on the job today, and I just thought we'd have a discussion about a problem that's plaguing my industry. We're on a truck. It's an Isuzu. We're looking at the CB antenna there at the moment, and it's actually been mounted fairly near the back edge of the roof, but there's a metal roof here. It has a ground plane. Okay, over here we have an aerial without a ground plane, or without a counterpoise. Now I've measured this aerial. It measures 600 millimeters in length. That's a Pacific base. It's mounted right beside the roof here, so there's generous reflected power coming from the side of the roof, as well as the fact that there's no actual ground plane underneath this antenna. So this would probably qualify as a terrible aerial install. I don't know what the VSWR is like, but it will be bad for those two reasons. First of all, there's no ground plane, and a quarter wave whip on a quarter wave whip mounted without a ground plane is not a resonant antenna, so it will have high reflected power. In this case, the antenna hasn't even been trimmed to length. And the third thing is wrong with it is this generous amount of metal which is right beside it, which will be providing reflected power as well.
Now, it's an installation, yes. The adjacent metalwork right here, between here and here, will have an adverse effect on the antenna's VSWR. And what we end up with is a radiation issue. We get perhaps relatively good radiation in that direction and extremely poor radiation in this direction. The high VSWR generated here, between here and here, can also result in other issues. Some radio manufacturers within their radios have built in a VSWR warning or a VSWR monitoring circuit. If the VSWR gets too high, in some cases the transmitter protects itself by reducing the transmit power. Let's just talk about that for a minute. So here's our transmitter over here, and there's a cable feed going up into this antenna. Built into the output stage of this transmitter is a VSWR detection circuit. It's not at all interested in the forward power. What it's very interested in is the reverse power. And in some situations, if this reverse power gets too high, this circuit feeds back to the transmitter, and instead of putting out 25 watts, it winds the power back down to a smaller transmit power. I'm just going to throw a figure at it. It winds it down to, say, 10 watts. So if this reverse power here detected in this circuit is too great, the transmitter is not even producing 25 watts, it's only producing 10. It may actually produce less than 10, because this detection circuit progressively winds the transmit power back down as this VSWR gets worse and worse. And that's done quite deliberately to protect the transmitter. But if you install an aerial like this, it'll have high VSWR from the outset. And you might think you're producing 25 watts and transmitting it, but you're not. You're producing a somewhat lower power. Combined with the fact you've got radiation, good radiation in that direction and very poor radiation in this direction. And now you might ask yourself the question, who would be silly enough to do this? Unfortunately, it's an issue I come across on a regular basis, and I think that's generically because there's a poor understanding of how to install an aerial and what an aerial is there to do. In some situations, aerials are installed like this for entirely nebulous reasons. I came across a situation where an aerial was installed just like this, simply because the vehicle was actually garaged in a situation where the tip of this antenna was scratching the roof. So rather than actually have this antenna, which was a quarter wave whip in actual fact, up where it should have been, over here, mounted in the middle of the roof, the antenna was shifted to the side and mounted halfway down the side of the vehicle, so that there was about a 50mm gap there. And that was done deliberately to preserve the paintwork on the roof. The entire radio system became a complete farce. There's a better solution here, and why it was never adopted, I have no idea. Leave the aerial where it was, in the middle of the roof, where it can get 360 degrees of radiation right around. It has good VSWR, there's no adjacent metalwork. There's this situation here where the body of the vehicle is nowhere near the active element of the aerial. And to solve the problem with the antenna scratching the roof, a sheet of Hippolon or some other scratch resistant surface could have been secured to the roof of the garage where this vehicle was garaged, or this vehicle was parked. That would have been a better solution. But it's just an example of a lack of understanding about aerials and aerial systems. And the transmitter has a feed which is going into this antenna. Now, how do you know that you've got an issue? Well, the fundamental thing you need to know is the forward power and the reverse power. The best way to determine that is with a VSWR meter. And we'll talk about some examples in a minute. In fact, I might take the camera down to my workshop and show you some examples. Essentially what we're going to do is we're going to put in here a meter. This meter is going to fit in line between the transmitter and the aerial. The meter will have some sort of indication on it, and it will have a method to determine the direction that you're measuring your power in, whether it be forward like that or reverse like that. There's another way of actually dealing with this issue, and that doesn't involve a transmitter at all or a VSWR meter. What you can do is you can actually sweep this with an instrument. I have an Anritsu Sightmaster, which is very valuable from this perspective. And the Anritsu Sightmaster will give you a graphical indication of, so there's no transmitter involved here. It will draw a graph. You sweep the antenna between two frequencies and you set up the scale on the side of the graph to give you an indication of its VSWR as a ratio. Now obviously down at the bottom, a ratio of 1:1 is a perfect antenna. You might have this as bad as 2:1 or 3:1 up the side here. Let's go 2:1. And a typical plot will look like this. At the center frequency here, you will have a relatively ideal VSWR. It will not be 1:1, but it will be quite close to 1:1. And then either side of this, you will have a rising VSWR. Okay, what we're going to do now is we're going to take an opportunity to have a look at some VSWR meters. Because I'm an old school guy, the first meter I purchased was this one. It's a Tallywave. Now the Tallywave meter is quite a useful meter. It's a wide band. Well, could call it wide band anyway. It has a fairly broad frequency range. Once you get outside its frequency range, there's a calibration chart on the back of this meter. You can see that it actually has a power switch here on the front and a forward and reverse switch also on the front. So the meter connects in between the set and the antenna. And it was my go-to meter for a short period of time. Very useful meter. Better than nothing, that's for real. I then purchased a Bird 43. Now the Bird 43 has been an industry standard for a number of years. They're built like the brick proverbial, if you know what I mean. They're a very rugged meter. Again, it's an inline meter, so we've got a connector on each side. The aluminium module, the aluminium plug here, is a transport plug. It's there specifically to short out the meter contacts to prevent the meter movement from thrashing about when you transport the meter. Now I purchased with this meter a large number of modules. They're in a range of frequencies and powers, and very useful to have, because the module operates over a fairly narrow frequency range. It's much more accurate than my Tallywave. Now I've pulled the module out here just to have a quick look at an example. This is a 25C module. It's probably the most common module I use. It's 25 watts, 100 to 250 megahertz. That inserts into here. A little spring clip keeps it in place.
using that module we can now measure quite accurately forward and reverse power. Now in addition to a range of modules, I also purchased a 50 ohm load. Now a 50 ohm load's quite important because you can hook your transmitter to this side of the meter, put your 50 ohm load onto that side of the meter, and ensure that you have full forward power, 25 watts in that direction, and because it's a 50 ohm load, you should have little to no power in the reverse direction. And by doing that, you can actually prove your coax cable setup. What you then do is you then take the 50 ohm load away and you install your aerial that you wish to test into that port there. And now this meter stood me in good stead for quite a few years, but there are probably better alternatives now, and this is probably one of them. This meter is quite readily available online. It's a Shawcom SWR meter. Obviously, again, it's got two ports, so it's going to go in line between the transmitter and the aerial. Now, if you're purchasing a meter, I highly recommend that you ensure that the meter specification, or that you're not operating the meter outside its specification. And in this case, the maximum power I can pass through this meter is 120 watts, and the frequency range is 125 megs to 525 megs, so it covers the lion's share of the VHF and UHF band. This meter gives you an additional reading, which is your transmit frequency. We'll give that to you in megahertz. Very useful if you don't know what your transmitter is actually sending up the aerial. Unfortunately, it doesn't give you forward and reverse power as such. It actually gives you VSWR as a ratio. So if you need to know what your forward and reverse power is, you will need a chart. Now, there's plenty of those charts available online, and if you easy enough to print one off, and that'll give you your forward and reverse powers if you want to know them specifically. Obviously, an SWR ratio of 1 to 1 is perfect. 1 to 1.5, well, it's getting worse. 1 to 2, and I would be saying no, we'll have to have a closer look. Now, if you're wanting to be really professional, of course, it pays to have some method of looking up an aerial without a transmitter. Now, this is an Anritsu Sightmaster. It's an S113, model S113. It's only black and white. You can get these in colour now, but you of course can pay a small fortune for the colour version. This doesn't require the use of the transmitter. This has inside it its own sweep set. So obviously it's going to output a signal from the port, and the reflected energy is also going to come back into the same port, and the meter actually will draw the plot of the VSWR curve, and it's unlike the meters over here, which is giving you an SWR measurement at a specific frequency. This thing is of course letting you know what the VSWR is across the entire band, so it's actually very useful. The SWR of course will be as the SWR increases, it runs up the side here, and frequency along the bottom. Now, you may have noticed in the picture I've got an aerial laying on my bench. This aerial is actually the reason why I started this video. I had a customer approach me, and he was less than satisfied with the service that his radio provided. This antenna was being used in the EN band. Now the EN band goes from 150 to about 155 megs. So a quarter wave whip at those frequencies should be in the region of 500 millimeters. However, this particular antenna is 650 millimeters long, and obviously the installer, or should I say bolter-oner, simply went to the store and grabbed an aerial and bolted it on. So not only was this not adjusted for length, but although this is a quarter wave whip and requires a ground plane, you can tell from the bracket that it's been bent and I've removed it. This antenna on the vehicle was installed in a location where there was little to no ground plane at all. So this antenna was removed and a ground independent antenna was installed, and I'm happy to, and that ground independent antenna, by the way, was checked using the site master to ensure that it was performing correctly, and I'm happy to report that the client is now much happier than ever before, with a more than doubling of his radio range as a result. Now, unfortunately, this issue is not rare in my industry, and I would say beware the bolter-oners, bearing in mind that the radio system as a whole is highly dependent on the performance of the antenna. The best advice I can give, I guess, is that if your installer is not or doesn't have this type of kit at all, then he's just a bolter-oner, and you'd be much better off finding a more highly qualified radio installer.